Okay, good morning, everybody. It's 10 sharp, so I think it's time to start this webinar about getting started with the new Mahti supercomputer at CSC. My name is Jussi Enkovaara, and I work in high performance computing support here at CSC. Some practical issues. First of all, this webinar will be recorded and published a bit later on in our YouTube channel. And if you have any questions, please use the chat. I try to monitor the chat also during the presentation, but latest at the end of the webinar, I will try to answer any questions that you have. So it's nice to see so many people interested about Mahti. So I think we start to go on. Here you can see the brief contents of this. So first, I'll give a very short overview about Mahti, what kind of system that is, and then we look a bit how to run programs in Mahti. Try to make few examples, demos, then a bit if you have your own software or you want to use software that's not available in Mahti, how to build programs, and at the end we go to some bit more deeper technical details. And as you hopefully know, all the user documentation can be found in docs.csc.fi, and I try to go by now and then also here and see where you can find things. For example, the brief getting started guide can be found just from the front page of this documentation site. First thing, of course, you need to get access to Mahti, and as with all CSC services, you can do that via our customer portal my.csc.fi. If there is already existing a CSC project, project manager can just apply for Mahti service there, and the participants of the projects, they still, after that, they need to apply the terms and conditions for the Mahti usage in order to actually be able to log in there. If there is not a CSC project yet, project manager can apply for a new project, add users, etc. And there is relatively good and straightforward documentation under the accounts, how to create a user account, how to create a new project, how that member the project and add services to the project. And once the user has gotten access to Mahti, you can just use SSH in order to log into Mahti. If your local user ID is different from the one of Mahti, you should provide the user ID here. For me, it happens to be the same, so I can just say SSH mahti.csc.fi, and if you have a SSH key set up, you will be just get access to you will connect there, otherwise a password will be prompted for you. Mahti, it's as the Finnish name suggests, it's quite a big, impressive machine, I would say. It has a bit over 1,400 compute nodes, and the nodes are equipped with the AMD ROM CPUs. There are 2 CPUs per node, and each of these CPUs has 64 cores. So in total, there are 128 cores per node, and about a bit over 180,000 cores in total. AMD CPUs, they support simultaneous multi-threading, which means that in some circumstances, a single physical core can run concurrently 2 threads. We discuss that a bit more later on, so it will depend a lot on the application whether you actually get any benefit from that. But that just means that in some circumstances, applications actually see that there are 256 cores per node. The clock frequency, the base frequency is 2.6 gigahertz, and depending on the sort of load on the CPUs and within the node, that can be boosted up to 3.3 gigahertz. Memory, there is 256 gigabytes per node, and contrary to Puhti, the system is homogeneous, so all the nodes have the same memory configuration, which is can be a bit smaller than the largest memory nodes in Puhti, but should be fine for most workloads. The interconnect between nodes is InfiniBand HDR with a maximum of 200 gigabytes per second of bandwidth. And the work disk lustre parallel file system for data during the simulations is 8 petabytes in Mahti, so a bit larger than in Puhti. The disk system in Mahti is very similar to Puhti. So there are basically 3 different directory areas. There is the home directory. Then there is a scratch directory for more temporary data storage and for larger data storage. And then there is a Apple directory. And all these directories are shared for the project, so all the project members by default can see all the files and directories there. You can of course manually change the permissions so that not everything is necessarily visible. There is the same tool than in Puhti that can be used for finding out all the directories the user has access, so the CSC workspaces. So for example, I belong at the moment to a couple of different projects. So there is something related to CSC user maintenance, something to the HPC support, and then there is actually also some project I'm giving some user support. And you can also see that what's the sort of capacity, what's the maximum, how much is used, and also in terms of number of files. The default quotas for these areas are same as in Puhti. So that's 1 terabyte for the scratch and 50 gigabytes for the Apple. But if you need more, you can via my.csc.fi, you can apply for larger quota. If you have been using our supercomputers previously, Taito and Sisu, they had the same file system, a shared file system, which means that you could directly access all the files in both supercomputers. That has some good sides, so easy access, but that has also some sort of disadvantages. So there is in principle single point of failure. So if there are problems with the file system in one computer, that affects also the other one. And that's one of the reasons that now with the Puhti and Mahti, the disk areas are separate. So anything I have in the Puhti or Mahti is not directly available in the other one. So data needs to be moved between them. There are two basic tools or approaches one can use, especially if you have a large amount of data which you think should be maybe preserved for a longer time, maybe also shared to other places than Puhti and Mahti. Using Allah's data service might be convenient, but if you just need to quickly copy something from Puhti to Mahti or vice versa, you can use the rsync command. You can find some examples for the rsync also in the docs. I can just look as an example here. So I'm now in Mahti. I can go to my Scratch directory. Let's go for this. Sorry, actually, that's the one I was about to go. I have here a directory for Mahti webinar, and there is basically a single executable, but not any data. And if I need to get some data from Puhti to here, I can first of all copy here the directory I want to copy into. Then I could open another terminal or just log out from here and go to Puhti. I can go to and you see that I have here a directory which has some sort of data also in that. And if I want to copy that directory to Mahti, I can use this rsync. -a means that, for example, for directories, copy also the contents and preserve all the timestamps. In order to make the transfer faster, I can use a compression, and I also want to see the progress, and this gives also possibility to continue the transfer if it has been interrupted. And then, okay, I give the name of the file or directory I want to copy. Place where I want, and then I have this copy pasted directory here, and okay, you get some output here. If I log out from Puhti, go back to Mahti, you can see that there is now also the my results directory containing the data. And if you look also the sort of, you can see that this we created they're just empty files a bit before starting the webinar. So timestamp is when they were created in Puhti and not when they were created in the or copied here to Mahti. So that's the basic way how to move data, and of course it works exactly symmetrically if you need to copy from Mahti to Puhti. Module system is in principle exactly the same as in Puhti. So it's the LMOD system. It's also hierarchical, so availability of modules can depend on which modules you have loaded. There is some standard set of modules when you log in, compiler, MPI environment, and a plus library. And in order to see all the available modules, you can use the module avail, and that shows you in principle all the modules that are compatible with this GCC environment. In order to see all the possible modules, you can use the module spider. There is much more output, much longer, because it's not only those that can be used with GCC. And let's say if I would like to use Chromax to do some molecular dynamic simulations, I could just use module.chromax, and module list then shows that okay, Chromax is now also available here. And if you have been using our previous supercomputers there, this works just the same. For running applications, again, things are in many cases similar to Puhti. So there is the same Slurm batch job system. Biggest difference is that Mahti is really targeted for large parallel applications that really need lots of floating point performance, need very capable interconnect. So in Mahti, you always allocate full nodes. So you do not normally specify how many MPI tasks or how many cores you want to use, but you specify how many nodes you want to use. If you go to docs, under computing and running jobs, you can get some basic information on, if you haven't used CSC supercomputers before, you probably, for this creating Puhti batch jobs, it has a more thorough example how this whole Slurm system works. And then if you go to create Mahti batch jobs, there are some sort of more Mahti related details. And as said, really the biggest difference is that when you are allocating resources, to specify how many nodes you want to use. If you are using a pure MPI program, then you should also specify that you want to use all 128 cores from a node. So in this case, with 2 nodes, you would be running in total with 256 cores. Due to very high number of cores per node in Mahti, if the application supports hybrid MPI OpenMP parallelization, it's very likely that it will perform more efficiently than pure MPI. And for the hybrid jobs, you should again specify the number of nodes, but then you specify with n tasks per node that how many MPI tasks per node you want to use, and with CPUs per task, how many OpenMP threads per core you would like to use, so that these two numbers should multiply up to 128. So let's try to make a simple example. Here are some ready-to-use snippets that one can just, actually you can just, I think if I click this one here, this will be copied to clipboard. And if I now go to Mahti, I should be able to directly pass this one here. So let's make some existing projects. So similar to Puhti, project needs to be always specified here. I'll be doing some small scale testing, so I will be using the test partition, and time 1 minute. 1 minute is okay, and I will be just playing around with one node to illustrate some things, and then I can with the srun I can launch the program. I had here this simple hello program. So, and if I now submit that one, it shouldn't take too long. You can see that there is the default output. Which seems to be still empty, so it might mean that this is still running. Okay. And apparently I have either some problem here or some nice demo effect. Okay, now it has completed, and if I look to output, we can see that this basically prints out that the MPI rank and threads, so all the thread IDs are 0 because that was not pure MPI job, and we can see that there are 2 different MPI tasks and cores that it was running in. Okay, there is the question in chat that is it possible to use half a node in Mahti? I'll come to that a bit later on. So you always allocate full nodes, but how many cores you actually use per node, that's up to you to decide. And it might be that if you have an application that requires, I mean, there is only 2 gigabytes per core of memory available. And if you need more memory, you might want to run with, let's say, half a node, which then means that you will have 4 gigabytes per memory. So that's possible, but the billing is always based on the full nodes, and allocation is always done in full nodes. So let's look at that a bit later, how to actually use subscribe the nodes. As said, applications can benefit from the hybrid parallelization. So in that case, one should specify the both n tasks per node and CPUs per task. And typically, you also specify the number of threads if you're using OpenMP with this OMP num threads environment variable. So let's modify our batch job script a bit. I just removed the old one here to make space for, and so now we are using only 16 MPI tasks per node, but we want to use 8 OpenMP threads per each MPI task. So 8 times 16 equals 128. And there is this environment variable, the slurm CPUs per task. Of course, one could by hand put here value of 8. This would be perfectly fine, but probably it can be easier to use these environment variables, so you can more easily, you need to, if you play around with the number of threads, these CPUs per task is the sort of only thing you need to modify. And let's try to run that one. And just wait a bit, it shouldn't take too long. And now you can see that in addition to MPI ranks here, we have also some threads. So for the rank 0, there are 8 different OpenMP threads. And one thing you can also see here is that when using this OpenMP, in principle, the operating system is allowed to move the CPU core where the threads run. So these threads, they are not bind to specific core. So for example, this says here that it can actually run on any of the cores with ID from 0 to 7. This one can run any from 8 to 15. We'll look in a moment how to actually bind the threads to specific cores, because in some cases that can give you more performance. But before going that, let's see how we can actually utilize the simultaneous multi-threading. So let's say that, okay, I know that my application would benefit from that one. Some applications we know that we have experienced that actually can benefit quite a lot. This, for example, CP2K when using hybrid functionals can give quite much more performance, but it's, as said, it's always up to application, and also what sort of optimum ratio of these tasks per node and CPUs per task, that really dependent on the application. So something you should experiment on your own. So now 16 times 16, that equals 256. If I try to execute that, however, by default, this simultaneous multi-threading is not enabled, because I mean there are some you can accidentally make some mistakes. So that needs to be specifically turned on. And we can once again go to the docs and look. Here is the example with the simultaneous multi-threading. So there is this SPatch hint multi-thread that needs to be specified if you want to use this functionality. So let's add that one. And if I now submit the job, you can see that, okay, now it succeeds. And if we look for the output, you can see that, okay, now there are 16. Actually, with sort, I can see that easier. You can see that, okay, there are 16 threads for each MPI task, and the numbering of these cores goes so that the IDs from 0 to 127, they are all the physical cores, and then the IDs for the sort of additional hardware threads, so on these logical cores, they start from 128. So for example, these thread 0 in MPI task 0. It can run on any of the 8 physical cores using either of the logical cores there. As already mentioned earlier, many applications actually work more efficiently if you do not allow the threads move between the cores. And there are some environment variables. First of all, if you want to check for your own application that sometimes the libraries or applications might be doing some binding of threads to core themselves. But there is, if you go to performance checklist here, there is one useful setting. So I can set these 2 environment variables for OpenMP, OMP affinity format, and they will be also displayed. So if I add these to my batch job script, I can actually, in this case, add the by default the stand error and stand out of the job. They are put in the same file, so I can put here sort of specific file where to get the data, and actually I can use the job ID. I think that was the correct setting for that one. And if we execute or launch that now and wait for a while, we can see that there is this stand n now, and so we see also the similar printout that the previous one that was done by this hybrid hello program. This is done by the OpenMP runtime environment, so it doesn't actually show you MPI process IDs, but it shows what's the real process ID, so it doesn't go from 0 to 1, but from some number, typically still by increments of 1. And we can see that, okay, again here the threads are allowed to sort of run on any of these 8 different cores. So let's try to bind that. And once again, we can look in the example scripts, how to do that. Oh, there is this setting OMP places, so we want that they will be running on individual cores. Important caveat here is now that with the current Open Plus linear algebra library there is a bug there, so that actually doesn't work currently with thread binding. So if you are using this Open Plus OMP module, you should not be using this setting I'm demonstrating here. So let's add this setting here, and if we now submit this one, and look you can now see that, okay, thread 0 can run only in the core 0, thread 1 here in core 1, and when we go to the sort of further MPI process, it goes on. So, and in many HPC type of workloads, this can actually give you at least 5 to 10% more performance. Once again, something that you should experiment with your own application. About the batch job partitions, so we have the test partition where you can run up to 2 nodes, up to 1 hour. And then we have the medium partition where you can run for 36 hours and up to 20 nodes. The time limits stay a bit shorter than, for example, in Puhti or previous supercomputers, but that's really to ensure that especially large-scale parallel jobs, they get good enough throughput from the system. And as already discussed, you always allocate only the full nodes. And okay, there was in chat this continuing question that if someone allocates 2 nodes but uses only half the cores, the other cores, they won't be available. So nodes are always exclusive to the job, so no one else can use them. If you really have a highly capable parallel application that can utilize more than 20 nodes, we have a large partition that allows you to run up to 200 nodes. However, in order to get access to that, you need to do scalability testing. I will discuss that shortly. And then for even more special cases, in connection with the forthcoming Grand Challenge goal and Grand Challenge projects, there might be possible to run with more or less half the machine with up to 700 nodes. And as said, the billing is always based on allocated nodes. All the jobs have access to all cores and memory and node, but may choose to run with fewer cores for better performance. There won't be a long-run partition, at least currently. That's not planned for Mahti. And the time, that's the wall clock time. So the full CPU time is, of course, then the number of cores you are using. Billing is actually based on node hours, so it's that's how it's counted for Mahti. But this time limit, this is wall clock time. In order to access the large partition, project manager can do the application in the customer portal, and you will be granted automatically a 30-day test period. And purpose of this period is that you can test how well your application scales and performs in Mahti, and then after this testing, you should submit your performance results for evaluation by CSC experts. And once they have confirmed that the performance is good enough, you will be granted the sort of production access for this large partition. Once again, you can find the instructions. They are in principle available here under accounts, how to access Mahti large partition. And if you look the available partitions for Mahti, you will find here also the link to the instructions. In brief, what you should be doing, you should use input case that resembles the actual production case. You can make it shorter for benchmarking, so number of iterations or time steps doesn't need to be same as in the actual production runs. And then you should run with at least 3, possibly 4, or maybe even more, depending on the case, a different number of nodes up to your scalability target. So if you think that you would like to use up to 100 nodes in your production runs, you should do some couple of runs before that limit and look how the code performs. Ideally, you should aim to something like 85% of parallel efficiency, but I think the minimum that will be accepted will be around 75%, meaning that if you, as an example, if you double the number of nodes, the running time should decrease at least by a factor of 1.5. CSC can give you assistance in improving the performance, or if there is any other need you need for getting the sort of large simulations running. So you can via service desk you can ask for help, especially if you see that okay, you are almost you're very close to the sort of good scalability limit. It might be that there are some relatively simple tricks that we can help you to achieve that. Yeah, there is a question also that will jobs with the shorter time limit have a shorter queuing time? Most likely yes. So there is similar to Puhti, there is a backfilling algorithm which tries to optimize the access to system. And just a simple example, let's say that if there is a request for a large number of nodes, and of course the Slurm at some point it will need to sort of start to empty the system to provide enough resources for the large job, and it can, based on the number of the jobs that and their time limits are running, it can estimate that okay, how long it should take for getting everything ready for this large job. And of course it's very likely that some nodes become available before all the nodes for the large job are free, and if there are sort of smaller jobs, maybe not even that high priority than the large job, but request only for a short time, the system can see that okay, these jobs can be executed in between. So having the time limit as realistic as possible is that will help you to sort of get a better throughput from the queuing system. There is the similar SF tool actually in the Mahti and Puhti that can give you some hints about how well your code is performing. So for this toy code, you can see that okay, there was one node used. It actually shows all the 256 cores there, even though you are not using all of them. And it shows you also that okay, how efficiently you were utilizing the CPU and how much memory you were actually using. So this was not using practically any memory at all. So you can see that it was using only 0.03% of the all available memory. As the allocation by default is done by full nodes, there is of course can be need for, cases where you need to do some post processing that take more time than it's, or might need just a few cores, something that cannot or should not be done on the login nodes. So very similar to Puhti, login nodes shouldn't be used for anything heavy. So if it runs more than a few minutes, if it uses more than a few gigs of memory, you should actually do also the pre and post processing in a batch jobs. But for this kind, there is a special interactive partition in Mahti where you can use only smaller amount of cores, and where actually if you use, let's say, only one core, the other cores from that particular node will also be available to the other users, so you're not allocating full nodes in this case. And there is maximum of 8 cores a user at the moment can use, so if in principle you can have 8 one-core interactive jobs or 1 8-core job. And there is similar tool than in Puhti, the S interactive, which probably it's easiest to use with this minus I flag. It will ask about, okay, which project I want to use, and then for how long time there are some defaults there, how many cores I want to use, default is 2, and now I have a sort of interactive access here, and if I need to run something, I should use the srun here. I could be running my hybrid hello here. And as you can see, there was sort of 2 threads available here and only one MPI task. So that's something if I needed to do some pre or post processing, which take more than few minutes and uses more than or uses few cores. I can exit that one, so that also ends the allocation. And if you have a sort of too many interactive jobs going on, or too many cores preset for interactive jobs, you will receive an error message. Here we have some of the examples already discussed. As there was this question about using only half the cores, I guess we can go. Okay, let's discuss the building applications first. So at the moment we have the GNU, AMD, and Intel compilers available there, all available as modules. And as discussed, the GNU compiler is the default. We have only one MPI environment, the OpenMPI here. And let's say if I wanted to use the AMD compilers, that's via the CLang module. You can actually also see that the Chromax is not compatible with the CLang, so it has been compiled with GCC, so it's now inactive. And we can see that, okay, we have now the CLang, OpenMP. I could use the CLang compiler command or flang compiler command to build C or Fortran applications now with the AMD compiler. There is also Intel compiler. With Intel compiler, you will be using the MKL linear algebra library, so OpenClass is inactive. If you go to the docs in compiling, you can find some sort of instructions and recommended compiler flags for different compilers. And once again, it really depends on the application which compiler works best. AMD Fortran compiler is maybe not as stable as the GNU and Intel ones. So if you have a Fortran application, there is some likelihood that it won't work correctly, but it still might be worth trying. I think in the best or easy cases, you get practically the same performance from all of these, but then in more special, I think we have seen examples where any of these compilers can be faster than the others. For the high performance libraries, they are available as modules, and most libraries are provided both as single threaded and multi-threaded versions. And the multi-threaded versions, they have the OMP. So we have the CLang here. I could also load the AMD Bliss library. So that's sort of AMD version of linear algebra, but there is also available special OMP version there, where the library will be utilizing multiple threads. If you have a pure MPI code, then it's of course you should be using the single threaded version, or if you have a hybrid MPI, OpenMP code, where you call libraries from multiple threads, use single threaded version. Then on the other hand, if you have a hybrid MPI, OpenMP application, where you're, let's say, in your own code, you use threading, but then libraries are called only from single thread, then you probably want to try these multi-threaded versions of libraries. Okay, let's go a bit deeper to the hardware of Mahti compute node for the last part of this webinar. So we already discussed that each node has two 64 core processors, also capable of running simultaneous multi-threading, and these support AVX2 vector instructions, which means that they can execute, each core can execute or calculate 4 double precision additions or multiplications with single instructions. For the memory hierarchy, there are 3 different caches, L1, L2, L3 caches. L1 and L2, they are private per core, but L3 is always shared among 4 cores. And if you use the simultaneous multi-threading, okay, these threads, obviously they share the L1 and L2 caches. The Mahti node, that contains 2 sockets, and so in each socket you have a one CPU, but from memory-wise, each socket is then divided into 4 different memory domains. So these non-uniform memory access NUMA domains. And then within each socket, you have these so-called cluster complex dice, and they contain then these so-called CCX core complexes, which share a sort of a different amount of things. So this is actually quite highly hierarchical architecture. For most applications, the really biggest thing to know about hierarchy is that 4 cores share the L3 cache, and then the differences between sockets and NUMA domains. So even though the memory is shared between all the cores, the latency and bandwidth vary whether you're accessing memory from the same NUMA domain or within the same socket. So some examples about latencies and bandwidth is that if you are accessing memory within this NUMA domain here, which is shared by 16 cores, the latency is about, to accessing memory is about 80 nanoseconds, bandwidth is bit over 40. Within the socket, so between two NUMA domains, within a socket, latency goes a bit higher, bandwidth a bit lower, not drastically, but especially at the moment when you need to go between the two sockets. So this actually is typo, there should be socket 1 here. The latency and bandwidth, they actually go up quite a bit. When you are using the full nodes, the biggest effect this might have is that whether you are binding the threads to cores. Because, of course, if the operating system is allowed, let's say you have allocated 8 threads per MPI task, and if the operating system is allowed to run them in any of the 8 first cores, it might be that, for example, thread 0 starts to run in one core, but then later on, if the operating system moves it the core that doesn't actually share the same L3 cache, it might be that the performance will be degraded. More relevant this probably becomes when you start to sort of run fewer than you are not running with the full node. So we can actually look that there was this question that can you run with the half nodes. So if let's take this batch job script and say that, okay, I'll take for now on, I just comment some of these. So let's say that, okay, we have a pure MPI job which needs more memory. So we want to run only with the half node. And we don't specify here anything. I can achieve that by commenting that out. So that's not considered here at all. And I can to make sure that it's not running multi-threaded. I will put the number of threads to 1. And let's see what happens when we execute that. So we're allocating the full node there still. Other users cannot run the other cores. We will be built based on a one node, but we say that we only want to use the 64 half the cores in this particular job. And if I look now at the, okay, so probably still running, okay. Okay, this was now probably, yeah. Let's sort that to make it. So what we actually see that because we asked only for 64 MPI threads, so 64 MPI tasks, what the Slurm does by default that, okay, it places them to the 64 first cores. In principle, application works correctly. All the MPI tasks, they can access 4 gigabytes of memory, but because of they are all sort of placed here, they will be all sharing the memory buses here. They might not be able to get the sort of full bandwidth out of that. So of course, if there are some physical buses here between the memory controllers here, and if you have everybody is sort of put here, it's possible that you do not get the full memory bandwidth. Then on the other hand, for the MPI communication within the node, you might get the better results. So once again, something to experiment. But let's say if you would like now to use so that, okay, you distribute your MPI tasks to the both sockets over the whole system, there is some additional thing you need to know and do. So when Slurm is placing the sort of the MPI tasks there, it actually places them CPUs per task apart, which means that in most cases, even if you were running here a pure MPI job, not using any threads, you probably would like to here specify so that in this case, CPUs per task, which would mean that the MPI rank 0 will be placed on core 0, MPI rank 1 will be based on core 2, etc., etc. So that if we execute this now with this kind of Slurm configuration, once again takes some time to execute. So you can actually see that now they are distributed evenly here. So there is this is the reason you're seeing both 0 and 1 here is that this is actually not the pure MPI program I'm running, so it's sort of a hybrid MPI OpenMP program only run with one thread, which means that because there are 2 cores visible for this rank here, the operating system would be allowed to switch between the first 2. So I can add this binding setting here. This wouldn't be any issue with the pure MPI program actually. Yeah, so it was. And now you can actually see that, okay, because of this placement here, so we are distributing now the job evenly to the full node. And let's say if you have a application that that is really it's not the performance is not limited by the sort of CPU power, but the memory bandwidth. It might be that you actually get some cases better performance, not just in a way that you can access more memory, placing on, let's say, one MPI tasks per NUME domain. And okay, as we have 8 NUME domains, we would have n tasks per node equal to 8 here, and you want to place them 16 CPU cores apart. So with the CPU task, and still okay, running with only one thread. Other thing that might be for some cases to get performance, as we saw here, that the L3 cache is shared among 4 cores. So in order to get the full bandwidth per core from L3, it might be that, okay, you would like to run not just a single task per domain, you could also, per NUME domain, you could also run some threads within NUME domain, but still so that each thread is getting the whole L3 for its own. And that you could achieve so that, okay, once again, we would like to have 8 MPI tasks, so 1 task per NUME domain, and we would like to have them placed 16 cores apart. But then we can say that, okay, actually, we still, within these MPI tasks, there are 4 of these core complexes with the single L3 cache within NUME domain. So we could say that, okay, yeah, we want to run with the 4 threads per this MPI task or NUME domain. And we would like to be so that they are spread, so that they are not sharing the L3 cache. This is starting to get quite complex, I know, and I guess this is starting to be really the sort of most complex example we discuss here. So 8 MPI tasks, 1 per NUME domain, separated by 16 cores, and then let's run 4 threads per each of these NUME domain, and with using this OMP proc bind spread, the threads within the MPI task and within this NUME domain will be distributed as evenly as possible. Let's run this one. And now actually I should have the information also in the. So as you can see from the output, there is 1 thread running on the core 0. Then next thread is running in core 4, so that will be with the different L3 cache. Next one will be running in core 8, which has still its own L3 cache. So all of these are now separated by 8 cores up to the end of the system. Okay, yeah, and there is a comment from Miguel that, for example, lumps, it seems to show best performance really with this 1 MPI task per NUME domain and 16 OpenMP threads. And I said this is very dependent on the application, might be also dependent on the workload actual input case. I have been running with a couple of different codes in Mahti. With CP2K, for example, I already mentioned then that if you're using the hybrid exchange correlation functionals there, the simultaneous multi-threading gives you lots of benefit, and you get a lot of benefit also from using quite many threads per node. So I think at least 16 to 32 threads per core seem to be working better than lower numbers. Then with some different input cases with CP2K, for example, not using the hybrid functionals, simultaneous multi-threading deteriorates the performance, so you get the worst performance with that, and also the optimum number of threads per MPI task is also much lower. So this is always something that you should experiment with the particular application and the particular input data set. Final thing, this probably won't affect most codes, but at the point when you really start to work on the scalability limit of, let's say, beyond 100 nodes, this might become relevant. How is the network topology in Mahti? So yeah, there is this infinite band HDR. The MPI latency is something like 1.3 microseconds per each link there, bandwidth of 200 gigabits per second. And the topology is arranged so that the all nodes, they are arranged to 6 different groups. So in the so-called Dragonfly Plus topology. So each group then contains some bit over 200 nodes. And then within the within this group, there is a so-called fat-tree topology, and all these groups, they are connected with all-to-all links. We don't have that much real sort of benchmarking how this affects the performance when you really run in large scale. We know from some other systems in Europe that has this similar type of architecture and topology, that in some cases, if you are running with huge number of nodes, there could be some benefits for limiting the runs within the Dragonfly group here. But as said, not something that at this point we have not much experience, and I guess that even when we got some special applications to use more of this really high node count, something that might be investigated and instructed a bit more. Okay, this is pretty much everything we had to present you about Mahti at this point. So in order to get to access, if you don't have yet, you can do that from my.csc.fi. User documentation starts to be also regarding to Mahti, starts to be in quite good shape. I would say you can look in the application listing here, whether your applications is actually ported to Mahti. The list of supported applications, as Mahti is a bit more a special purpose, that will be more limited. And of course, due to the requirement that the applications should use a minimum of one node, 128 cores, and not, there are lots of widely used and important applications that are used more in throughput like schemes with lower core counts, and they won't be supported in Mahti. On the other hand, once we get some of the bigger workloads moved from Puhti to Mahti, of course in Puhti there will be more room for these smaller scale applications and runs. Thanks for all the comments and questions by far. If you have any further questions at this point, I would be happy to answer them. Okay, if not, I thank everybody for participating. As said, the recording will be made available in our YouTube channel. You have in the chat the link, and if you have any feedback concerning this particular webinar or suggestions for future webinar topics. We appreciate a lot any feedback that you can give us. You can find the feedback link also in the chat at this point. About slides of the presentation, I think we can share them also in this webinar page, so we can make these available. So thanks for participating. I leave this open for a while so that if you want to access the feedback there, provide the feedback, it will stay open there, and I hope you have productive moments in utilizing Mahti. Thank you.